All right, in this video, we're going to get into some analytic geometry and talk about the area between two curves. So we're just going to start out looking at something that we already know how to do. Region R is bounded by the graph of y equals 6 square root of x equals 1, and x equals 9. Find the area of R. Okay, so we can do that. We're going to just use an integral, right? That's what we've been learning about recently. So we're going to integrate 6 square root of x as x runs from 1 to 9. And so that's going to involve finding an antiderivative, plugging in the top and bottom, and subtracting. You see me do this many times. You don't need to talk you through the arithmetic. But we go through all those steps, and we get 104. Okay, but if we look at this more closely, and I ask what other line is part of the boundary of R, we see that, okay, we've got those two lines, the vertical lines, the curve y equals 6 square root x, but we've got a bottom of this region as well, the x-axis. And that's kind of what we had said at the beginning when we started to integrate. It was like, okay, well, the integral represents the amount of area between the curve and the x-axis. Okay, so really our question today is, what if the bottom of the region wasn't the x-axis? Okay, but if we look closely, really what we've been doing is what we're going to be doing here today the whole time. See, when we go back to the idea of the Riemann sum, which is what I'm going to be continually doing throughout this unit, we see that we're adding up these really thin rectangles, right? And their height is going to be 6 square root x minus 0, top minus bottom. That's going to be a theme, but I'll get more into that in a minute. And so we see that we could equivalently write this integral as the integral from 1 to 9 of 6 square root of x minus 0 dx. You might not be seeing why I would want to do that right now, but I think that'll become more clear in a moment. Now let's think about what would happen if we actually had two curves that were, bounding a region. So suppose I've got this f of x and g of x, as x runs from 0 to pi over 2, and then the vertical line x equals pi over 2, and that's bounding my region called E. So if we wanted to find the area of region E, we could probably set up integrals to do that right now. We could just, be clever about it and say, okay, well, I think I'm going to just, take this whole area, the integral of f, and I'm going to subtract away the area under g. Okay, so I'll take the whole highlighted area and then subtract away the red area. So that would be like, okay, the integral from 0 to pi over 2 of f of x dx minus the integral from 0 to pi over 2 of g of x dx. Okay, and you might notice, okay, well, we're integrating with the same variable on the same bounds. We could combine those integrals, so we had to do less plugging in and subtracting, I guess really the same amount of plugging in, less subtracting. I guess unless there was like terms in the formulas for f and g. But anyway, we could combine these into one integral, and maybe it'd be a little faster. We could say that's the integral of f of x minus g of x dx. But then that kind of brings up the question, well, what this is a nice region in the first quadrant. What would happen if, part of it was under the x-axis, or maybe the whole thing was under it? Would we have to worry about, like the area being negative or whatever? And what I'll say for now is kind of like we did before, when we're talking about the area of a region, that's going to be a positive number. Right? But the definite integral of a function can be negative if that function is, negative over that interval. Okay, so what I'm going to say is that actually this formula is not going to change if the region moves around. It's we're going to be integrating top minus bottom is what I'm going to show you here. And I think to convince you of why it's always going to be top minus bottom, I might just take it off to the side and just try to convince you. So I might ask you, what's the distance between these 2 points? Okay, and if, we're looking for a vertical distance of, 2 points that are separated only vertically, right? They've got the same x-coordinate. We could find that vertical distance by doing 10 minus 5, and that would equal 5. And think about, what if I just, moved these points around so that they were still separated vertically, but one of them was underneath the x-axis, one of the y-coordinates went negative. Well, you can see there's still going to be a distance of 5 between these 2 points, and we can see that by taking 2 minus negative 3 and getting 5. And then to hopefully just really hammer down the point here, if they were both underneath the x-axis, and it was like 4, negative 1 and 4, negative 6, these points are still separated by a distance of 5, and we can see that by taking top minus bottom. Okay, so really, what's the distance between the 2 points? I would answer with just that, top minus bottom, y2 minus y1. And that's going to be something that will help us, understand the formula, get a usable formula that we can kind of use repeatedly and move forward and solve other types of problems. So to really see how this formula is working, we're going to go back to the idea of the Riemann sum, and I'm going to draw a replica of our region. I'm going to do that a lot when we're doing these geometry type problems. I'm going to draw a replica of the region. It doesn't have to be perfect, as you can see, but it's showing the general situation. Okay, and I'm going to draw a representative rectangle. That's that blue slice in the middle there. And then I'm going to take it out and think about, the y coordinates of the top and the bottom, right? Because I'm going to be doing top minus bottom. Okay? And then if I really think about it, what this is this is the rectangle that I'm adding the area up of in a Riemann sum. So I might say, okay, I've got this rectangle, and its area, it's an area of a rectangle, it's going to be height times width. And the height of this rectangle, the distance between the 2 points, that's going to be f of x minus g of x. But what's the width? Right? It's been a while. Remember, the width is like some really small change in x, and so we just call that delta x and write it really small. Okay, but that small area we've got, one rectangle that we're going to add up a bunch of them to get the whole area, that would have height f of x minus g of x and width delta x. So as the number of these rectangles goes towards infinity and their respective widths go towards 0, okay, our Riemann sum would become an integral, and this area is going to be given by the integral as x goes from 0 to pi over 2, right? Because that's the different places that these vertical blue rectangles could slide back and forth on. And we're going to be adding up a bunch of rectangle areas. So the height of these rectangles is f of x minus g of x, and the width is delta x. And so as, width of the rectangles goes towards 0, that becomes a dx, and then there we get kind of the formula we were expecting to get, the integral from 0 to pi over 2 of top minus bottom dx. All right, now here it says, f is e to the x and g is cosine x. Find the exact value of the area of g. Okay, that's not, all that new to you computing an integral, but I will show you how it would go just in case you were curious. So, we had said it was the integral from 0 to pi over 2 of f of x minus g of x dx. So we're just going to plug in on that. We're going to need to find an antiderivative, but that won't be too hard. It'll be an antiderivative for e to the x minus an antiderivative for cosine x. And then I'll let x range from 0 to pi over 2. And then I'm going to, plug those values in and subtract. When I plug in pi over 2, I'd get e to the pi over 2 minus the sine of pi over 2. And then I'd plug in 0 and get e to the 0 minus sine of 0. And I'm subtracting this stuff, and I get a minus 1 and another minus 1. And so that would be e to the pi over 2 minus 2. Alright, so a pretty typical example of this is like, hey, find the area of the region bounded by the parabola y equals negative x squared plus 3x plus 4 and the line y equals 4 without a diagram. And, sometimes these problems come with diagrams, oftentimes they don't. I'm going to frequently not give you a diagram so that you have to create one yourself so that you're in the habit, because once we start doing the volumes, you really will need to be doing the representative rectangle to keep your radii straight once we turn it into radiuses. So, what I'm going to do, I'm going to sketch the parabola and the line. This is a downward facing parabola and a horizontal line. Okay, you need to know that the line y equals 4 sits horizontally. Okay, so we're going to need to know the places where these two things intersect. So I'm going to label them appropriately and say, okay, I want these 2 points of intersection. And in order to find those, I'm going to need to set the two things equal to each other because they got the same y coordinate at those points. So I'm going to say, y equals negative x squared plus 3x plus 4 is going to equal y equals 4. And then I'm going to start solving. And it's like, oh, okay, if I subtract 4 from both sides, okay, this thing looks very factorable. And then I can find, oh, okay, x will equal 0 or 3, and those are going to be my intersection points. Okay. Then from there, I need to think about, top and bottom, because that's going to be my integrand, the thing that goes in my integral. So I'm going to draw a representative rectangle and kind of take it off to the side and say, okay, on top, I've got negative x squared plus 3x plus 4, and on bottom, I've got y equals 4. So I'm going to take top minus bottom for my height of my rectangle. The width would be dx, and so start an integral. Okay, yeah, I might actually subtract those first. Yeah, because you don't want to be doing plus 4x and minus 4x in our antiderivative. That's not going to be what we want to do. So I set up my integral, and it's going to be the integral from 0 to 3, and I'm going to do, okay, top minus bottom. The height of my rectangle is negative x squared plus 3x, and the width is dx, so I guess I'll put that in first, but okay, there you go. Negative x squared plus 3x. And this is something that we can find an antiderivative for this pretty easily. Negative 1/3 x to the third plus 3 halves x squared as x goes from 0 to 3. And I'll plug those in and I'll get negative 1/3 of 27. That's negative 9 plus 27 halves. And then I will plug in 0 and I get 0. And so I'd get negative 18 halves plus 27 halves. That's 9 halves, I think. Okay, and that's a pretty typical one. There's some other ones, but a lot of these allow the use of a calculator. So I'm going to show you one of those right here. But this one's a little different. I think we've done enough. Here's two curves, find the area between them. You could do this with a calculator if you need it. Find the value of k for which the vertical line x equals k splits the shaded region into two equal areas. So it basically cuts it in half. And so I'm going to draw you a picture of that. I don't know if this is exactly accurate, but I'm going to say it probably favors the right side a little bit. And I'm just going to say, okay, that's x equals k right there. That's two equal areas, same amount of area on both sides. Okay, and if that's the case, then what we know is that the integral from 0 up to k is going to equal the integral from k up to 2. Okay, so that's really what I'm going to start with because that's kind of the structure of the problem. Two equal areas. And then I'm going to need to think about what goes inside that integral. So it's going to be kind of top minus bottom. If I think about it, before the green line and after the green line, it's the same curve on top and the same line on bottom. So I only need one representative rectangle. I'm going to take that off to the side and think about the height. That's going to be top minus bottom. So on top, I've got x squared plus 2. And on bottom, I've got negative x. Okay. And so if I actually subtract those, x squared plus 2 minus negative x, I could write that as x squared plus x plus 2. So I'm going to integrate top minus bottom dx on the left, and okay, it's the same rectangle on the right, so it'll just be the same integrand. Okay, and it's like, okay, we haven't really had to solve too many equations like this in this class, but I suppose we could. And what we'll do is we'll just anti-differentiate, so 1/3 x to the third, 1/2 x squared, and 2x as x goes from 0 to k, and that's going to be equal to, well, the same antiderivative because it's the same integrand, as x goes from k up to 2. And so I'm going to plug some stuff in. As you can see, it's not all that exciting. I'm going to notice, oh, wait, I have 1/3 k to the third and negative 1/3 k to the third on the other side. So I'm going to kind of add all those like terms together and get 2/3 k to the third plus 1k squared plus 4k on the left side and then 26/3 on the right side. Okay, that's weird. And then I'm going to go over to Desmos at this point, because this is not the type of equation we have the ability to solve by hand. If it was, set up just right to do group and factor, maybe we could, but that's actually not a factoring technique you're required to do in AP Calculus. So a third-degree polynomial like this is probably going to be a calculator question. So we're going to go over to Desmos to help us solve this equation. All right, so in a Desmos window, I've got these two equations preloaded, and I'm going to say, now, there may be a way you can have it just directly solve the equation. I'm relatively new to using Desmos for AP Calculus, and I am not the best at solving these equations, but I know that this intersection technique will work. So I'm going to turn on these graphs, red and blue. Okay, 26/3, that's 8 and 2/3, so that's a little bit higher up. I would need to zoom out. Okay, and then I will, okay, I don't think there's nothing at the bottom of the screen you would need to see. It's covered up by a white square, but I'm going to tap the intersection and see, okay, that's going to be the x coordinate at which these two things are happening. Well, I used x instead of k, so I'd say k equals 1.331. Okay, clearly display my answer, and just remember that when we are solving an equation using the calculator, using Desmos, we have to write down the equation that we solved. So that equation right here was, really important. Now, I suppose we probably could have gotten away with even the line above it, right? Because we probably could have plugged that into the calculator and found an intersection for that as well. But we need to have some sort of equation when we come up with an answer. Okay. Now, what would we do if the curves intersected more than twice? Okay, that's something that we need to consider. So I might ask you to consider these curves and ask you to sketch the graphs after we look at them on Desmos, right? I don't need you to be able to factor f. We don't know how to sketch that because we can't factor it. If we can factor it, then we can sketch it, but we can't factor this thing, so we're going to need some technology help. So I'm going to go in here and I'm going to load f of x and g of x into Desmos, and I'm going to ask it to graph them. Okay, and then I'm going to, move it around a little bit and see, okay, I've got a third-degree polynomial and a line kind of cutting through it and giving me two different regions. Okay, so if I want the total area, I'm going to probably need to take two separate integrals, unless I can be very clever. And maybe we'll figure out how to do that in just a minute. Okay, so I think I'm going to need to figure out these intersection points. So I'm going to, kind of call for all of these to be remembered, and okay, so we've got x equals 1, x equals 2, and x equals 5. Okay, so I think that's enough for us to go back and draw a sketch. So I'm going to say, okay, I've got this third-degree polynomial looking curve and an upward facing line, and it intersected 3 times at x equals 1, x equals 2, and x equals 5. And if I want to find the total area bounded by the graphs of f and g, I'm going to need to be careful because top and bottom are switching. Okay, at first, f is on top and g is on bottom between x equals 1 and x equals 2, but then it switches, right? And g of x, the line, is on top of the curve from x equals 2 to x equals 5. So I'm going to need to take two separate integrals. And so I'll say it first, I'll just say the red area is going to be the area between x equals 1 and x equals 2. And so top minus bottom would be f of x minus g of x. And then after x equals 2, between x equals 2 and x equals 5, I'm going to talk about the blue area, which would be something I would get by integrating g of x minus f of x, because top minus bottom, line minus curve. And if I wanted to find the total area, I would just, like as of right now, I'm trying to just run two separate integrals. So the red area would be f minus g, and the blue area would be the integral of g minus f. Okay, but, just to make this easier on myself, I've already used a calculator to make the sketch, I really believe, and for a penny and for a pound, might as well use the calculator. Let's go back and compute these integrals. All right, so I'm back here. I'm going to integrate from 1 to 2 on f minus g. Okay, I'll call that a. Okay, it's going to give me 0.58333. And then I'll integrate from 2 to 5 on g minus f. Right. There, I'll show that to you. And then I could find the sum of those two things by adding them together and doing a plus b. And so I do that and scroll and see, okay, 11.833. Okay. Seems reasonable enough to say, okay, 11.833. But you might be sitting there thinking, I might know of a better way. And there is a better way. If we've got the use of the calculator already, then we might as well just have it always consider these heights to be positive. And I could do that by taking the absolute value of f minus g and just having it always return positive. Because really the issue is, like, if I integrate from 1 to 5, it's just part of the time I'm getting positive numbers and part of the time I'm getting negative numbers, right? And we want the total amount of area, so we need everything to be counting positively. We've kind of run into a situation pretty similar to this in the past. Okay, so I'm going to say, if we've got the use of a calculator already, we could say that this is the integral of the absolute value of f minus g, as x just goes all the way from 1 to 5. And I'll show you if we go back over here and just switch up what we're saying to, now, hey, find me the integral of the absolute value, we're going to get that same 11.833 number. Here's a similar multiple choice question. So which of these is going to represent the total shaded area? Yeah, this one's pretty easy, but what we need to do is think about, okay, we're just going to need to add two integrals, as we can see from the answer choices. We're just going to think about top and bottom and where is which one on top and which one on bottom. So at first, I've got curve and straight line. Okay, and the curve is f of x, and I look, and that straight line is y equals negative 3. So I'm going to have top minus bottom, f minus negative 3. Okay, so that probably is actually going to be enough to narrow it down to c already, but we can keep going and really understand why it's c. If we look at the other part, it's going to be top is the line, bottom is the curve, so negative 3 minus f. And then that's what we're going to see in answer choice C, and so we're going to bubble that and kind of call it a day. And I think that that's going to be enough examples for this video. We've done the area between two curves expressed as functions of x. We've found the area between curves that intersect at more than 2 points. I'm going to come back and show you how to find the area between curves expressed as functions of y in the next video. So that's going to be all for this one. Thanks for watching.